All right, welcome. In this video, we're going to talk through the answers to the timed FRQ option number 3. And in this first part, and so again, all together, these questions should have taken you about 15 minutes. That was the goal, is to practice this with time. If you have not actually done these questions, then please pause the video and go do these questions and practice it for time first, and then come back and analyze your responses. All right, so for A, we are going to try and explain why this substance has a higher boiling point than COS. And if you take a look here, they show you the molecular structure, and we need to identify all the intermolecular forces in each compound. So when we're trying to figure out the intermolecular forces, the IMFs, the first step is to look at the polarity of the molecule, and the structure is already given to us. They both look linear. CS2 looks totally symmetric though, so it's going to be nonpolar. Whereas COS, this looks asymmetric, right? They've got an oxygen side and a sulfur side. There's going to be differing electronegativities, so your molecule is going to be polar. If a molecule is nonpolar, it experiences dispersion forces only. If it's polar, it experiences dispersion forces and dipole-dipole. And notice how it says to identify all the intermolecular forces in each compound. So for this question, I think they're really looking for you to say dispersion and dipole-dipole with this molecule right here, and not just dipole-dipole. And then you want to explain why CS2 has a higher boiling point than COS. Initially, you might say, hey, dipole-dipole is stronger than dispersion, so COS has stronger intermolecular forces. But if you look at the data, it's actually the opposite. This one has the higher boiling point. Though if it has a higher boiling point, that tells you that it has stronger IMFs. So when I answer this question, first of all, I want to identify all the intermolecular forces. So I want to say that CS2 has dispersion forces and COS has dispersion and dipole-dipole. I would actually maybe write out the word dispersion on test day. Okay, and then it looks like the dispersion forces in CS2 are actually stronger than the dispersion and dipole-dipole in COS. And we know that because of the higher boiling point. The reason why it ends up having that stronger force is because we know that dispersion forces are proportional to size. So as you increase the size of the molecule, and by size we're thinking about like the size of the electron cloud, then the dispersion forces are going to increase in strength. So let's look at some examples of what this would look like. Here are the scoring guidelines. So you get 1 point for identifying the intermolecular forces in both molecules. And they're saying CS2 has dispersion, COS has both dispersion and dipole-dipole. It looks like they're looking for all of these things. I'm not quite sure if you left out the second dispersion, if they gave you the point or not. But if all you said was that COS has dipole-dipole, and that's all you said, then that definitely would not earn the point. It's really important in these comparison problems that you need to mention both molecules. Okay. So mention both IMFs, both molecules. And then 1 point for a valid explanation. So in this example, the London dispersion forces in CS2 are stronger than the combination of dispersion and dipole-dipole forces. And in this answer, looks like they weren't even looking for an explanation of why that is. They're just looking for a statement saying the dispersion forces in CS2 are stronger than the dispersion and dipole-dipole in COS. So all we really needed was like this part right here. So state what the IMFs are. So identify the IMFs in both molecules, and then make a comparative statement about their relative strengths. Here are some examples here. We end up with having if you look at this one, the boiling point is higher because of its relative size, creates a stronger dispersion force. So which is stronger than the combined IMF present in COS. It seems like they get that there's more than one IMF here, but they didn't specifically state it. So I think this question would earn the point for the comparative, but not earn the point for clearly identifying both sets of IMFs, because at some point we need to say, this substance has dipole and dispersion, this substance just has dispersion. And in this case, the both COS and CS2 have London dispersion, and COS also has dipole-dipole. So they earn that point for identifying all of the IMFs present. So make sure you account for all of them. And then because of the size, there's a more polarizable electron cloud. Polarizability, this is something that you will see popping up related to dispersion forces. So the reason why larger molecules have stronger dispersion forces is because their electron clouds are more polarizable. So that's a word you can throw in your explanation. You don't have to include it. Like, it's okay if you didn't, but if you want to throw it in there, that's great. And it's another keyword you can look for in a question stem. If you hear mention of the polarizability of an electron cloud, then they might be, you want to think about dispersion forces. So just kind of, you can cue for that word there. So it has a stronger forces. So identify what the forces are, make a comparative statement. And yeah, so that's that one. And then this one, what is the pressure? And we're given a volume, we're given a temperature, we're given a mass, which we can convert into moles, and we're trying to find pressure. So this looks like a PV equals nRT scenario here. So we're going to rearrange that, and we're going to solve for pressure. Some things to keep in mind in a Pivnert calculation is pay attention to your units of R. In this context, I don't think they specified what pressure unit it had to be in. I can't really see behind my little box here, but the R values varies with pressure. So there's one R value that has units of atmospheres and one that gives it in torr, which is otherwise known as the millimeter mercury. And you need to make sure that your temperature is in Kelvin, your volume has to be in liters, and you have to convert your grams into moles here. And I will show you an answer here. So we converted our grams into moles, and then we plugged that into PV equals nRT here. And we have the same setup. We got slightly different numerical answers on some of these ones. With sig figs, you should end up with 2 sig figs in your answer because your volume only has 2 sig figs in it. And you never know which question you're going to be graded for sig figs on. So this might be a question that they were assessing for sig figs on, or maybe they weren't grading for sig figs on this one, and you would have been just fine if you'd put like 0.699. I think in this question, I think they actually did not grade for sig figs on this one. So if you put 0.7 or 0.699, you still would have gotten the full points. But the breakdown here is you get a point for calculating the moles correctly, and you get a point for using those moles to find the pressure. And if you had calculated the moles incorrectly, let's say you got, 5 moles of CS2, and as long as you use this answer correctly in the second part of the question, you could still earn these points right here. So if you're not sure how to do part of a question, just do your best, make a guess, right? Make something up if you're not quite sure. And then as long as you use that answer correctly in later parts of the problem, you can still earn those later points. All right, here's a question with an experimental setup. So it definitely involves some reading and taking a look at the data for what this setup is. And it looks like a calorimetry experiment. And this is the kind of setup where the thing you are reacting is separate from the water. And we're doing the calorimetry experiment. We want to do Q equals mc delta T. We want to calculate the amount of heat absorbed by the water. So if you imagine your setup here, you're taking the temperature of the water. There's your thermometer. Okay. And I want to draw that in there because when we're doing the MCAT calculation, it's important that you use the mass of whatever you are taking the temperature of. So in this case, you're taking the temperature of the water. So you want to make sure you use the mass of your water in your MCAT. So the mass of the water is 125.00 grams. And they're going to be looking for the fact that you don't want to include the 0.55 here, because the 0.55, that's separate, right? They don't mix together. CMAs are staying separate here. So just use the mass of the water alone. If this were a scenario where you're mixing two reactants together into the same container, then you would use the combined mass. But in this scenario, the masses stay separate. So I'm going to use the mass of just the water. And then the specific heat is given to us. And if you look at the temperature change, it's always good to stop and write down what the temperature change is there. In this case, this temperature change has 3 sig figs in it. But you can stop and check your sig figs with your temperature change. And then when you solve for Q, you end up getting 15,200 joules. And if you, so I just want to write down what this temperature change is. This is 29.1, 3 sig figs. The question asks us, though, to find the energy in kilojoules. So I want to make sure I convert that into kilojoules. And my answer should have 3 sig figs. So if we take a look at our responses, looks like we all got the same response. But some people converted to kilojoules, some people left it in joules. And let's take a look at our data set. 1 point for the correct calculation. It's not entirely clear from the scoring guidelines whether, if you gave it in joules, were they going to dock you the points? Not sure. My guess would be if you labeled it correctly that you'd probably be okay. So if you labeled it as 15,200 joules, you'd probably be all right. But if they asked you for the answer in kilojoules and you just wrote 15,200 and didn't label it, then you definitely would not earn the point. But not entirely clear, but you probably would have been fine giving it in joules here. But they were looking for kilojoules, so make sure you read the question stem carefully on these types of questions. Now we're looking at, we're trying to find how much heat would be released if 1 mole was combusted. Okay, so if you take a look at what you know, there's some different ways of thinking about it, but what we can say is in this reaction, we released, 15.2 kilojoules of energy per every 0.55 grams combusted. So let's label this, it's C3H7OH. Okay, so what we want to do is convert this into energy per mole. So we could convert grams in per mole, and you can say that 1 mole of this is 60.09 grams, and then you end up with 1661 kilojoules per every mole that reacts. And if we want to round it to 2 sig figs, then what we do is we'd write 1700 kilojoules to 2 sig figs. So you're using your previous answer. And again, if you had got this answer wrong, like let's say you calculated that it was 20 kilojoules, as long as you used that wrong answer correctly in the next part of the question, you could still earn the full points for this part of the question. So keep that in mind. So here's some examples. We all got 1700 kilojoules. This one is kind of written out a different way, just kind of different order from the way I showed my calculation. So you can find out how many moles that is when we react 0.55 grams, and then take that energy and divide it by that many moles to find the energy per mole. So in these examples, they were all consistent in the way they solved that one. So yeah, 1700 kilojoules per mole. And let's see, this was just a 1 pole. Oh wait, sorry, wrong way. Here's the scoring guidelines. This was 2 points, and you got a point for getting the number right. And in this case, sometimes they do this and sometimes they don't, but in this case, they actually gave you a cue that, hey, we're checking for sig figs on this problem. So it turns out on this exam, this was the question where they assessed for sig figs. So they actually gave you a point for reporting the number with the correct number of sig figs. So if you'd reported it as 1661, you would have only earned 1 point out of the 2 possible. If you reported it this way, or this way is also fine, you would have earned the full 2 points. And then the last question says, what if we have a burner containing some water and we burn, the difference in mass is still 0.55. Will the final temperature be greater than, less than, or equal to what we got in the first experiment? So if we look in experiment 1, we reacted 0.55 grams of just the alcohol. In experiment 2, the 0.55 grams was a sample of alcohol contaminated with water. So if you think about what's happening here, really the mass of alcohol that was combusted here is not really 0.55 grams. It's going to be some smaller number, right? We don't know what the number is, but maybe, like, let's throw, if it helps to think of an example, maybe it's 0.5 grams alcohol and 0.05 grams water, right? Whatever it is, this number, the amount of alcohol burned, is going to be smaller than it was in the original experiment. So you're going to have less actual alcohol combusted. So we're going to have less heat released. So that change in temperature is going to be smaller, right? Because if you think about Q equals MC delta T, if you have, less heat released, you're going to have a smaller delta T. So the final temperature will be less than what we would expect it to be if it was really pure alcohol there. So that contamination, so this is an example of doing some kind of experimental error analysis here. And here's an example, burning the same mass would result in less of the alcohol actually being burned in experiment 2. So you end up with less energy produced. So your final temperature is going to be less than. So, and here's another way of phrasing it, because in the mass that we combusted, some of it's not actually combusted, some of it's just going to be water evaporating. And water evaporating doesn't produce that same amount of heat, so we'll get less heat. So that's another way of saying it as well. And this was just a one-pointer, so you had to have the correct choice with an explanation. So if all you said was less than and didn't explain it, you would earn 0 points. So both of these answers would both earn, that 1 point. You get full points there. And then the last question on here was a chromatography question. So we've got a chromatography chamber. Whenever you see a chromatography question, always pay attention to what the solvent is here. And because the way you interpret the data is going to be different if your solvent is polar than if it is nonpolar. So the first question says, which dye is the least polar? And justify your answers in terms of interactions between the dyes and the solvents. So if you look at the, let's actually look at the scoring guidelines first on this one. So the dye C is the least polar because it moved the furthest, and nonpolar dyes, so like you got a point for it's going to be in 2-pointer. So you got a point for identifying dye C, and then you got a point for your explanation. Your explanation needs to include a description of the interactions between the dye and the solvent, or you could also compare the interactions between the dye and the paper. So the solvent is nonpolar, and paper is polar. So dye C is the least polar because it moved the furthest, and you could either explain that by saying that it's more attracted to the nonpolar solvent, or you could say it's less attracted by the polar paper. And you could do either or on that option there. So now let me scroll back and look at these examples here. So in this one we said C, so we got a point for identifying it correctly. And we said because it traveled the greatest distance, but as I'm reading this question carefully, when it says you need to discuss the interactions, I am not sure whether you earn the points here because we didn't really discuss like the attractions here. So we did say we correctly identified it traveled the greatest distance with a nonpolar solvent, but the question wants us to think about the interaction. So think about like the level of attraction and whether it's more attracted to the solvent or the paper. And so here we said we correctly identified dye C. The solvent is nonpolar. Here, I think you'd earn that point because we mentioned the attraction. So just make sure you discuss the attraction of the dye to the paper, of the dye to the solvent. And then the unknown sample, which dye is present in the unknown sample, justify your answer. So dye A is the one that's in our unknown. So you get a point for identifying dye A. And then again, we've got kind of two options for your justification. And in this choice, if you just said dye A and had no justification, you could still earn 1 point out of the 2 in this case. So they're looking for is that the unknown is a position that's about midway between the origin and the solvent front. So if you remember that, we call that the RF value. So we say the RF value of the unknown is similar to what it is over here on the left. And that was the option here, is the RF is close to 0.5. So you just want to somehow just kind of look at this data and say, oh, it's traveled about halfway. If you want to, you can calculate the RF value. The RF value would be the distance that the dye traveled, so like the distance that the unknown traveled divided by the distance of the solvent front. So like if this distance right here was 2 centimeters, this one traveled 1 centimeter, the RF would be 1 over 2, would be 0.5. You didn't have to calculate the RF value. You could just say, oh, it looks like it traveled about halfway, and that's what dye A did. That's all they're really looking for there. All right. So those are our answers to this one. Hopefully that helps. Let me know if you have any follow-up questions.